Okay, so recording is started. So let us get going with. Uh, we'll just do a quick recap of unit heterograph. We did this in the last class as well, um, and then we'll talk about one final topic that is left in this module, so to speak, and then we'll work on quite a number of problems today. Okay, so we spoke about the linear theory where you assume that the response of a watershed to a rainfall event is a linear response, and therefore you are allowed to use the principle of proportionality and the principle of superposition to predict the response to other events which are not uh, a 1 centimeter rainfall event, right? So if I have 1 centimeter of rainfall, my response is so and so x, let us say. So if I have 2 centimeters of rainfall, my response will be 2 times x, whatever x is. Or if I have two rainfall events, so that is the principle of proportionality, right? So if the response for 1 centimeter is x, and the response for 2 centimeters is 2 times x, for 2.5 is 2.5x. That is the first one, principle of proportionality, which is an important aspect of the linear response of the watershed. And the second aspect is the linear theory of principle of superposition, which is that if I have two rainfall events, one happening after the other, then I can add the responses of these two events by superposing the solutions one after the other, and you add the two solutions, you get the response of the overall event, which need not necessarily be one event, right? It might be broken up into two events of different magnitudes, right? And so then we worked out so many different problems where, given a unit heterograph, we would estimate the response to different types of rainfall events, with base flow, without base flow, assuming base flow, and so on and so forth, right? Then the next thing we did was to figure out what is the unit heterograph. So the first type of problem was, given the unit heterograph, how to find the response to an event. The second type was, given the response to an event, how to find the unit heterograph. So that was what we did next, the derivation of a unit heterograph. So for that, again, we looked at different types of events, the isolated storms and the complex storms, right? So that was the second part of the unit hydrograph approach. Then we spoke about how to obtain a unit hydrograph of different durations given a unit hydrograph of a certain duration, right? And broadly speaking, there were these two methods that we use. The first is the method of superposition, where if I have a d hour unit hydrograph, I can find n times d hour unit hydrograph, subject to the condition that n is a integer multiple. N is an integer, right? So if I have a 2-hour unit hydrograph, I can find a 4, 6, 8, 10, 12, whatever hour unit hydrograph, right? Or if I have a 5-hour unit hydrograph, I can find a 10-hour, 15-hour, 20-hour, and so on. With a 5-hour unit hydrograph, I can't find an 8-hour unit hydrograph using the method of superposition. So the only limitation of the method of superposition is that the unit hydrograph that you desire can only be an integer multiple of the unit hydrograph that you have. Okay, that's fairly straightforward. The second method that we spoke about was the S-curve method, where the unit hydrograph that you desire can be any duration. It need not. It works even for an integer value, but it works for even other non-integer values. So if I have a 2-hour unit hydrograph, I can get a 4-hour unit hydrograph from the S-curve method. I can also get a 5-hour unit hydrograph, which is not an integer multiple, right? So we spoke about that, and we discussed how to go about doing that. And then we spoke about the synthetic unit hydrograph, the SCS triangular unit hydrograph that we spoke about. That was an example of a synthetic unit hydrograph, right? And then we briefly discussed, at least just conceptually, the idea of an instantaneous unit hydrograph. And when I say instantaneous unit hydrograph, what I mean is a unit hydrograph produced by an instantaneous excess rainfall event of 1 centimeter. Okay. Of course, 1 centimeter of excess rainfall cannot happen in an instant. So when we say instant, we mean about 10 minutes, let's say 10-15 minutes. Okay, some short duration and highly intense rainfall event happening in a very short duration, let's say 10-15 minutes or so, which produces about 1 centimeter of excess rainfall. That would be an instantaneous unit hydrograph. All right. Okay. So now we will we'll just quickly talk about another form of representing the unit hydrograph, which is called the distribution graph. Okay, it's very similar to the graph, and in fact, instead of giving you the runoff rates, you get what you get is not the rate of runoff, but the percentage of runoff in successive time intervals, right? So, for example, in the unit hydrograph, you will say, let us say, at time t equal to 0, the unit hydrograph is 0 cubic meters per second. At 2 hours, it is 5 cubic meters per second. At 4 hours, it is 8 cubic meters per second. At 6 hours, it is some other number, and so on, right? Instead of that, the distribution graph will simply give you the percentage of runoff that happened in every successive time interval, right? So, for example, you have this example shown here of all the runoff that is produced by that particular watershed. 5% of the runoff was produced in the first 4 hours. So that's what this is saying. Okay, just a second. Okay, so this 5 that is shown here represents the percentage of runoff produced in that time interval. So in the first 4 hours, on the x-axis, I have time 0, 4, 8, 12, 16, and so on. The first 4 hours, 5% of the total runoff produced by the watershed was produced in the first 4 hours. In the next 4 hours, 4 to 8, 10% of the total runoff happened in those 4 hours. And then in the next 4, 15%. And then the next 4, 27%. And then again, it starts to go down, right? 16, 12, 8, 5, 2, and so on. So this is an example of a distribution graph. Now, what you can infer from a distribution graph is that, something that's very interesting. Now, a distribution graph can be used to infer the unit hydrograph and also a direct runoff hydrograph. Okay, so the distribution graph is not just useful in terms of figuring out the unit hydrograph of a catchment. You can work backwards also. You can also use it to identify the direct runoff hydrograph. You don't have to go through 2 steps, right? So, for example, if I give you the distribution graph of a catchment and ask you to predict the direct runoff from this particular catchment due to 2.3 centimeters of excess rainfall, for example, okay, the percentage of runoff produced will be the same whether it is 1 centimeter of excess rainfall or 2 centimeters or 2.3 or 5.7, whatever it is, right? So what I'm trying to say is, okay, so let us say, so I have time on the x-axis and discharge on the, okay, so if I, let's say this is my, oh, sorry. Okay. Yeah, I've lost touch with this after getting back to, sorry about that. Okay, anyway, I'll figure it out. Anyway, so what I'm trying to say is, you take successive intervals. Okay, what I do is I compute the area under this first portion, the second portion, and the third portion, and so on, and compute the total area under that. So if I take, let us say, this first portion, if I take the area and divide it by the total area, so let us say the areas are A1, A2, A3, and so on. So the distribution graph is basically A1, A1 divided by sigma AI. That is the distribution graph. D1 is equal to A1 divided by sigma AI. D2 will be A2 divided by sigma AI. Or in general, you can say DI, distribution graph, for the ith time interval, is AI, which is the area under the unit hydrograph or the direct runoff hydrograph for that particular time interval, divided by the total area under the curve. Okay, so that is what the distribution graph gives us. So if I give you the effective rainfall hyetograph, I can derive a direct runoff hydrograph using the distribution graph. Okay, so it is merely giving us the distribution of runoff over a certain period of time. Okay, any questions? Any questions at all? Okay, so let's just go ahead and we'll take a look at this particular problem. Very interesting and a simple setup. So let's try to make the most of this. Okay, a catchment of 200 hectares area has rainfalls of 7.5 centimeter, 2 centimeters, and 5 centimeter on 3 consecutive days. The average fee index can be assumed to be 2.5 centimeters per day. Distribution graph percentages of the surface runoff, which extended over 6 days for every rainfall of 1 day duration, are 5, 15, 40, 25, 10, and 5. Determine the ordinates of the discharge hydrograph by neglecting the base flow. Okay. So again, this is one of those comprehensive problems which covers a wide variety of topics that we have discussed over a period of time. Okay. So the first thing is you're given a catchment of a certain size, 200 hectares, so possibly about the size of our campus. Okay, and the rainfall amounts over 3 consecutive days is given: 7.5 centimeters on the first day, 2 centimeters of rainfall on the second day, and 5 centimeters of rainfall on the third day. The fee index for this area is also given. So per day, I have an infiltration loss, an average infiltration loss of 2.5 centimeters per day. Okay, which means on the first day, how much effective rainfall happened? How much excess rainfall happened? Anybody? Who are the ones who are here? Okay. Revant, can you tell us how much effective rainfall happened on the first day? Revant G. Okay, Srividya, how much effective rainfall happened on the first day?
Sir,
Yes. I just heard, sir. I didn't hear the rest of the answer.
for the first day, 7.5 centimeters.
Of rainfall, how much of that becomes excess rainfall is the question. How much of that becomes runoff?
1 centimeter.
So the fee index, which is the estimate of the infiltration loss, is 2.5 centimeters per day. Okay, so in 1 day, 2.5 centimeters of infiltration will happen, right? I get 7.5 centimeters of rainfall. Out of that, 2.5 becomes my infiltration. So the effective rainfall or the excess rainfall or the runoff, all these things mean the same, right? Will be
5, sir.
centimeters. That's it. Thank you. Okay, Tarun, on the second day, how much effective rainfall or how much excess rainfall happens? Go ahead.
Uh, no excess rainfall. Sir. The infiltration, because the high index was more than the
Yeah,
rainfall event.
correct. Thank you. So, if I have an infiltration index of 2.5 centimeters per day, and if the amount of rainfall received is less than that, it's only 2 centimeters, then all of that water is going to infiltrate, which means no runoff will be produced on the second day. Thank you very much. Okay. Ishwar, on the third day, how much runoff would have happened? Okay. Venkatesh, 36, roll number 36. The other Venkatesh. On the third day, how much? Come on. On the third day, we get 5 centimeters of excess rainfall. Sorry, 5 centimeters of rainfall, out of which 2.5 centimeters is infiltration. So the depth of excess rainfall will be 5 minus 2.5. 2.5 centimeters of excess rainfall happens on the third day. Okay, so now already we have established that if I get a certain amount of rainfall, okay, someone wants to join this call. Okay, so we have now figured out how much rainfall, how much excess rainfall happens on each of these 3 successive days, given the total rainfall received on each day and the infiltration loss that is taking place over those 3 days. Okay, so now let's go to the next part of the problem. Okay, so infiltration loss on each day will be 2.5, 2.5, 2.5 centimeters each, which means we get an effective rainfall of 5 centimeters on the first day, 0 centimeters on the second day, and 2.5 centimeters on the third day. Okay, now let us go back to the problem statement and look at what is given to us. The distribution graph percentages of the surface runoff, which which extended over 6 days for every rainfall of one duration. Okay, so if I get some amount of rainfall on the first day, I produce runoff for about 6 days, right? So if I get rainfall for one full day, it produces runoff for 6 days. Okay, which means that what is given here now is in intervals of 1 day each. So 0 to 1 day, 5% of runoff. 1 to 2 days, 15% of runoff. 2 to 3, 3 to 4, 4 to 5, and 5 to 6. You have the percentages of runoff produced on each of those days. Okay, so that's what I'm going to list in the next. So that's why you will see 0 to 1, 1 to 2, 2 to 3, 3 to 4. The first column goes all the way to 8 to 9 days. Why do I go up to 9 days? Because I have 3 rainfall events. The first day is 0 to 1, and then 1 to 2, and then 2 to 3. So the third rainfall event will produce runoff until 9 days, right? So that's why I have my time, I have extended it up to 9 days. Okay, so that explains why my first column does not stop at 6 days. It stops at 9 days because the second and the third rainfall event will make the runoff extend until 9 days. Okay, so let's take a look at the distribution graph percentages. Okay, so now if 5 centimeters of effective rainfall happens due to the first day's effective rainfall, this 5 centimeter can be broken up into the different components on the 6 days, right? So if 5 centimeters of effective rainfall happens due to the rainfall on day 1. The distribution graph tells us how much of that 5 centimeters will happen on the first day, how much will happen on the second day, the third day, fourth, fifth, and sixth days respectively. So how much will happen on the first day? What is the percentage of effective rainfall that will happen on the first day? 5%, right? So out of those 5 centimeters, 5% will happen on the first day, right? So the distributed runoff for the effective rainfall of 5 centimeters, the first rainfall event, will be 5% of 5 centimeter. So 5 by 100 into 5 gives me this 0.25. Okay, 15% of 5 is 0.75. I don't know why this isn't working. There you go. So how do I get this? 5% of 5 centimeters is 0.25 centimeters. 15% of 5 centimeters is 0.75 centimeters, right? So 15 divided by 100 into 5 equal to 15 times 5, 75 divided by 100 is 0.75. So 40 by 100 into 5 is 2 centimeters, and so on, right? So that 5 centimeters of excess rainfall or effective rainfall is distributed over those 6 days in these fractions: 0.25 centimeters, 0.75, 2, 1.25, 0.5, 0.25. If you add all of this up, you will get 5 centimeter. Just check: 0.25 plus 0.75, 1, plus 2, 3, plus 1.25, 4.25, plus another 0.5 centimeters, that's 4.75, and then on the last day 0.25. So you add all of that up, you will get 5 centimeters of excess or effective rainfall distributed over these 6 days. Okay. Now, the second day's rainfall event, there was rainfall, but there was no runoff. There was no effective rainfall, right? So basically, you will be left with a bunch of zeros for the second day. No problem. But you see, I have lagged it by 1 day. So it started from the second row and ended on the what is that, 6 to 7 days. Of course, I've also put 7 to 8. Don't worry about that. And on the third day's rainfall event, it starts from day 2 to 3, right? Because that is the time at which the effective the rainfall started. So how do I get this number 0.5? How did I get this number? Anybody tell me how I got this number 0.125? Anybody, please? You can just unmute yourself and speak up, because
5% of 2.7.
5% of 2.5. Okay, so let's just do that. 5%, 5 by 100 into 0.25. Sorry, 2.5. I'm sorry. I'm so sorry. Right, 5% of 2.5. Where did this 2.5 come from? That is this 2.5, and 5% comes from here. So because the distribution graph is giving the percentage from the day of the rainfall event to the next 6 days, right? So 0 to 1, 1 to 2, 2 to 3. So you just have to take this 2.5 centimeters and distribute it in these ratios: 5%, 15%, 40%, and so on, over the 6 days, starting with the day on which the rainfall happened. The rainfall happened on the third day, 2 to 3, the second to the third day, in that interval. So from here, you start doing 5% of 2.5. The next day, you do 15% of 2.5, which is 0.375. The next day, you do 40% of 2.5, and so on, right? So you just extend that out from the third day onwards to the 9th day, right? So that is the way the the runoff gets distributed over these 3 days, over the rainfall events that happened over 3 days, over the entire duration of about 9 days. Okay, so that is the essence of this approach. Now, if I want to find the total runoff, what should I do? I just add these three columns. So on the first day, how much runoff will I produce? 0.25 centimeters. On the second day, I'll produce 0.75 centimeters. On the third day, I'll produce 2 plus 0 plus 0.125, 2.125. On the third day, it will be 1.25 plus 0 plus 0.375, and so on. Okay. But that will give me runoff in what units? If I add these three columns, I'll get units of centimeter. Correct? Because all these numbers are centimeters. It's 5% of 5 centimeter, 15% of 5 centimeter, and so on. Right? So these numbers are in centimeters. You add them all up, you will get the centimeters of excess rainfall. Okay? If I want to know the runoff rate, meter cube per second, what was the rate at which runoff was produced on the first day, on the second day, and the third day, then what do you think we should do? Anybody has an idea what we can do? Let us say, let's take the first day as an example. 0.25 centimeters of excess rainfall was produced on the first day. And my question is, what is the rate of runoff? Let us say the average rate of runoff from this particular watershed that can produce 0.25 centimeters of excess rainfall. How would you do it? Remember, what is given to us is the area of the catchment. 200 hectares is the area of the catchment. Okay, so keep that in mind and tell me what should be, how should I find out the runoff? I want units of meter cube per second. That is what we are used to, right? I want to know at what rate, on what average rate of meter cube per second will runoff be produced on the first day. So what should I do? Anybody? Okay, so let me just let me say loudly in my head what I'm thinking. Okay, so let us say I produce 0.25 centimeters of runoff on the first day. If I multiply that by the area of the catchment, what will I get? I'm just thinking out aloud. If I take the depth of runoff on the first day, 0.25 centimeters, and multiply that by the area of my catchment, that should give me the volume of runoff produced on the first day. Correct? So if the volume of runoff produced on the first day is known, if I divide it by the number of seconds on that day, so I have meter cube of runoff. If I divide that by the number of seconds on the day, that will give me the average rate at which runoff was produced on that day. Yes? Correct? So I'll take 0.25 multiplied by, okay, let me write over here, 0.25 divided by 100 into 200 hectares, 200 into 10 to the power 4. So this is in meter square. This is meters. I've divided by 100 to convert it to meters. So what will this be? 5,000 meter cube, right? 5,000 meter cube, is that correct? Yeah, it's correct. All right. So if 5,000 meter cube of runoff is produced on the first day, what is the average rate at which this runoff must have been produced? Just divide this by the number of seconds in the day. How many seconds in the day? 86,400, which is 24 into 3,600 seconds. 24 hours into 3,600 seconds per day. So can anybody quickly do this? 5,000 divided by 86,400. Quickly do it and unmute yourself and just say it out loud.
0.058.
0.058. Okay. 0.058 meter cube per second. Okay.
Yes,
That looks correct. 0.058. So that's 5.8 divided by minus 2 meter cube per second. Thank you. Okay. On the second day, it will be 0.75 centimeters. Convert that to meters. Multiplied by the area, you will get the volume of runoff. Divided by the number of seconds on the day, you get the average rate of runoff produced on that particular day. Okay. And so on. So the third row will be 2 plus 0.125, 2.125 centimeters. Convert that to meters, divided by 100 basically, multiplied by the area, you get the volume of runoff, divided by 86,400, you get the average rate of runoff produced on that day, and so on. So that's how the you've now figured out the runoff produced by this particular watershed. Okay. Any questions? Any questions at all? Okay. Let's go ahead and solve maybe a couple more problems. We'll do one more on distribution graph itself, and then maybe a couple more on we'll kind of a recap of the other concepts we've learned. Okay, take a look at this. Analysis of the surface runoff records of a one-day storm over a catchment yielded the following data, right? So the runoff, the flood hydrograph gives us these details. So you have time from 0, 1, 2, 3, all the way to 9 days. And the discharge produced on those 9 days is listed, and the estimated base flow is also given. Okay, so this is the information available to us. Determine the 24, which means 1 day. Determine the 1 day distribution graph percentages. If the catchment area is 600 kilometers square, determine the depth of rainfall excess. Okay. So yeah, what should the first thing we do be? What should I do as a first step? Anybody? Yeah. Veera Venkatesh, go ahead. What would you do? What would the first do? There's only the 5 of you left. Yeah, go ahead.
We have total discharge and estimated base flow. So, like, we have to initially get the, like, by subtracting, we will get the sur-
Correct.
surface runoff.
Very good. So we have the discharge, which is the combination of runoff and base flow. So in the next row, we are provided the estimate of base flow. Simply subtract the third row from the second row, right? What will be left is the direct runoff hydrograph ordinate. So on time t equal to 0 days, the runoff will be 0 because rainfall has just not started. The second day, at time t equal to 1 day, runoff will be 63 minus 22. You will get the direct runoff magnitude, and then 151 minus 25, whatever. So you just keep going all the way. At the 8th day, runoff will again come down to 0. 20 minus 20, you'll have 0. So if I have rainfall for 1 day, I produce a hydrograph that lasts for, I produce runoff that lasts for 8 days. It takes 8 days for the runoff to come down to 0. So rainfall for 1 day produces runoff that goes up, reaches a peak at, let's say, the second day, 151 minus 25, yeah, second day, and then it comes down to 0 by 8 days. So that's the first step I'll do, is to subtract the base flow from my flood discharge to get the runoff component. Okay, now that I've got the runoff component, what should I do next? Sriram, can you tell us what would you do next?
Sir, actually, we got the total runoff, right? I mean, in form of duration and the rate. So we had to calculate the total runoff volume and then divide with the area of the catchment. Then we can get the depth of rainfall excess, yeah, average.
Very good. So you've answered the last part of the question, right? If
Okay.
the catchment area is 600 kilometers square, determine the depth of rainfall excess. Very good. So what he said is, now once we subtract base flow from discharge and get the direct runoff hydrograph, you can compute the area under that curve. Correct? What will the area under that curve give us? It will give us the volume of runoff. If you divide it by the area of the catchment, you will get the depth of excess rainfall. Okay, so let me just represent what he has said. Why it doesn't work? Time. Now, in this case, it happens to be days in my discharge Q. So at t equal to 0, my discharge is 0. At time t equal to 1 day, discharge is 41. So let's say it's something like this. So sorry. $41. Next day it will be 126. So 126 maybe somewhere here. Sorry. Next one will be 105, maybe something like this. Then the next one will be 72, and so on. Okay, so let's not waste time on getting all these details right. As long as the concept is clear, okay, let's say this is what the hydrograph looks like. Okay, I'm just representing it pictorially. Okay, so what we can do is, so what Sriram said is, compute the area under this curve. You can easily compute the area under this curve. Area of the first triangle plus area of the next trapezoid plus next trapezoid and so on, all the way to 0. We know how to do that. You get the area under this curve after, of course, taking care of the units and all of that. So the x-axis is in units of days. You'll have to convert it to seconds, right? So multiplied by 24 multiplied by 3600, you will get the x-axis duration in units of seconds. Multiply that with meter cube per second, you will get meter cube, which is the volume of runoff. Then you divide that volume by the area of the catchment, which is 600 kilometers square. That will give us the depth of excess rainfall. Okay, wonderful. Thank you. What's the next thing we should do?
Sir, as we can compute the, I mean, in that particular time interval, the amount of runoff produced, we can, if we divide with the total runoff produced, then we can get the percentage rate.
Exactly. Thank you. So what he's saying is, let us say I compute this area, and then I have this area, and then I have this area, and so on. So in each successive interval, I know the area under the curve. Okay. So I know the area under the curve. I divide by the total area under the curve. So that's what I said. So the distribution graph for the ith interval will be area of under the ith interval of my unit hydrograph or flood hydrograph. I'm sorry, direct runoff hydrograph. Okay, so the distribution graph for the ith interval will be the area of the runoff hydrograph in the ith interval divided by the total area under the curve. So you would just take this area, whatever it is, divided by the total area under the curve. That will give the distribution graph percentage. Because remember, what I'm getting percentage, so both the numerator and the denominator must be in the same units, right? Only then they'll cancel out and you're left with a ratio which indicates the percentage produced in that particular duration. Okay, so the 24-hour distribution graph percentage will be available by simply doing this. Okay, so it's not at all hard. It's a straightforward calculation. You just do this and you're done. Okay, any questions? Any questions? Okay, shall we move on? We'll try and do one more problem today, and then we'll stop with that. No question. Okay, let's take a look at this. Okay, so now this is a standard problem. The ordinates of a hydrograph of surface runoff resulting from 4.5 centimeters of excess rainfall of duration 8 hours in a catchment are as follows. Right, so I get 4.5 centimeters of excess rainfall in 8 hours. So the excess rainfall amount is known, and the runoff produced is given here. And the question is to determine the ordinates of the 8-hour unit hydrograph for this particular catchment. Now, the way the unit this runoff hydrograph is given is in a very unconventional way. I don't know if you notice it, right? It's given in unevenly spaced time intervals. First 5 hours, then next 8 hours, then next 8 hours, then 7 hours, then 4 hours, then 3 hours. So it's not arranged in a very methodical way. Okay. So now, does this really make a difference in our procedure for how to find the unit hydrograph? Does it matter that the time is given in some kind of an uneven intervals? Does it matter? Anybody has any thoughts on this? Does it matter that it's not given in nice intervals? Anybody?
It doesn't matter.
It doesn't matter. Correct. It actually doesn't matter. Okay. It will matter if you have to do this S curve and all of that, because it assumes that you are the intervals are uniformly spaced. If you want to do an S curve method, right, it becomes easier if you have uniform intervals, because then you will lag the S curve, subtract it, and so on, and then it becomes really difficult. Suppose you have to subtract one unit hydrograph, one S curve from another. It's very difficult if the time intervals are not evenly spaced, right? So that is only applicable if you are doing any addition, subtraction, and so on. Now, suppose I give you, in this particular case, if I give you 2 rainfall events, okay, I say, in the first 8 hours, I received 2.5 centimeters of excess rainfall. In the second 8 hours, I got 3.2 centimeters of excess rainfall. Tell me the resulting flood hydrograph. Okay, then you will have a tough time, right? Because when you lag it, you have to take care of all these time intervals. It becomes very difficult. Okay, so this is not a typical situation. The reason people try to give those uniform intervals is that you can lag by some duration. It will be very, otherwise this makes life a little bit difficult to lag and do all of those things. Okay, that's all. So it's a matter of convenience. But suppose you have to do lagging, then you will simply linearly interpolate between these 2 points. So it will not affect your computations in the sense of the correctness of the answer. It will affect it in terms of the difficulty level. I mean, it's irritation, right? You just have to lag it. So you have to take care of all these intervals, and it has to be done in a very methodical way. So it is much more convenient if the time intervals are evenly spaced, but this does not prevent us from solving the problem. So what will you do in this case? What is the answer actually? The answer can be written in one sentence, in one shot. You just take all these numbers and divide it by 4.5 and you're done, right? There's nothing more you have to do. The discharge starts at 0 and ends at 0. So therefore, there's no base flow, nothing to remove. Okay, base flow has already been removed, or there was no base flow in this particular catchment. Okay, so what you have is just the runoff. The discharge is just the direct runoff. And how much runoff produced this? 4.5 centimeters. If 4.5 centimeters produces this, then 1 centimeter will produce whatever these numbers are divided by 4.5. That's all. Right? It's a straightforward problem, but there is some complication, or it looks like something that's complicated. Why are the time intervals not uniform? It really doesn't matter. Okay? Any questions before we stop for the day?
Sir, are you setting the test tube paper?
I already said that I am. I will, most likely I will share it with Roshan, and I think it'll be just, we'll probably discuss it together before setting the paper, but I think it'll just be me, most likely. Okay. Anyway, how does it matter? The concepts are the same. It's just a matter of who sets the question paper. Not a big deal, but it'll be me. Okay. But I mean, I want to give that. I mean, because he's going to take over, I will of course give it to him. He may feel like he wants to change something. If he wants to, then he'll change it. But it's unlikely. Okay, I don't want to say that it won't happen. At the same time, I don't want to say it will happen. Highly unlikely that he'll change the question paper, but he may discuss it with you. I don't know. Okay, so each teacher has their own style, right?
Thank you, sir.
Yeah. Okay, guys. Thank you so much. We will end for the day. We will meet again on Friday at 8 o'clock. So happy Dashara. Everybody have fun. Tomorrow is of course it's a holiday, Gandhi Jayanti plus Vijayadashmi. So have fun, everybody. I saw the pictures of that Garba night thing. It was so good. I wish I had been there. But anyway, it's okay. I couldn't make it on that day, unfortunately. So we will meet again on Friday, guys. So I would appreciate it if everybody can be present. Of course, the recording is available, so there is a strong incentive to just keep sleeping. But it would be nice if I could see you all on Friday. Okay? Take care, everybody.
Sir, unfortunately, we have midterm exams, sir. That's why we got less time.
Don't worry. It's okay. It's okay. No problem. No problem. I know midterm exams are there. And I know anyway recording is available, so there isn't really any incentive to attend. But do you have an exam on Friday as well?
Yes, sir.
Oh, you do?
We have a pre-elective.
Okay, pre-elective. Okay, okay. Some of you will have it. It's okay. No problem. I mean, I saw most of you, over the last few days. I think I've said bye to almost everybody, so it's all right. Okay. Take care, guys. See you all on Friday. Bye bye.